Intrinsic semiconductors. Objective: to study the characteristics of intrinsic semiconductors. We have already studied that semiconductors are substances having conductivity between that of an insulator and a conductor. Semiconductors are of two types: intrinsic semiconductors and extrinsic semiconductors. First, we shall learn about the intrinsic semiconductors. Intrinsic semiconductors are pure semiconductors. The common examples of intrinsic semiconductors are germanium Ge with a forbidden energy gap of 0.5 electron volts and silicon Si with a forbidden energy gap of 1.5 electron volts. Let us understand more about the intrinsic semiconductors by taking the example of pure silicon Si. In pure silicon at 0 Kelvin, the 4 valence electrons of each atom form covalent bonds by sharing electrons of the neighboring atoms. Hence, there are no free electrons in this crystal, and it cannot conduct any electric current. However, at room temperature, the atoms in the semiconductor absorb thermal energy, and the covalent bonds of a few atoms rupture, giving rise to free electrons. The escaping electrons leave vacant space known as holes. The free electrons move randomly within the crystal and conduct electric current when the crystal is connected in a circuit. Here, number of free electrons Ne equals number of holes Nh. That is, Ne is equal to Nh is equal to Ni, where Ni is known as intrinsic carrier concentration. A hole is filled by an electron of the neighboring atom, leaving behind another hole at its site. We can say that while the electron moves in one direction, the hole appears to move in the opposite direction. Similarly, an electron from another covalent bond settles into this hole, creating a hole at its origin. This process continues, and we can say that the hole, acting as a charge carrier, is moving freely from one atom to the other in a direction opposite to that of the electron. When an electric field is applied to an intrinsic semiconductor, the free electrons drift towards the positive terminal, constituting the electron current IE. At the same time, the adjacent valence electrons move into holes, effectively moving the holes towards the negative terminal of the battery, giving rise to the hole current IH. Thus, total current I in an intrinsic semiconductor is due to both the electrons and the holes. Mathematically, I equals IE plus IH. Thus, we have learned that the intrinsic semiconductors are pure semiconductors. In an intrinsic semiconductor, no conduction takes place at 0 Kelvin. The conductivity of an intrinsic semiconductor is due to the movement of free electrons and the holes. That is, I equals IE plus IH.